Every second, the global financial system generates terabytes of unstructured data. Prices fluctuate, accounts default, and liquidity pools shift across millions of interconnected nodes. While processing this volume is a baseline requirement, the primary task is navigation. A financial AI acts as a pathfinder, identifying specific sequences of actions within high-dimensional noise. This is a problem-solving agent. A problem-solving agent is a specialized goal-based AI that searches through a sequence of actions to identify a path toward a specific, desirable state. To navigate, the agent structures the chaos into a state-space graph. A state-space graph is a mathematical representation where current financial situations are mapped as nodes, and the decisions connecting them are mapped as directional links. Translating ambiguous banking goals into computable graph architectures allows an AI to evaluate millions of potential pathways and execute the most efficient route. Building this architecture requires breaking a problem down into 5 atomic components. We can map these using a standard debt recovery scenario. First is the initial state. This is the starting node, which in this case represents a retail banking account that is 90 days past due. Second is the set of available actions. These are the operational levers the bank can pull, such as triggering an automated SMS, initiating a manual phone call, or escalating to a legal hold. Third is the transition model. Because human environments are non-deterministic, actions have probabilistic outcomes. A manual phone call might only carry a 30% probability of securing a promise to pay. Fourth is the goal test. This is the strict condition for success. Here, the test returns true only if the account reaches a zero balance or the agent secures a legally binding settlement. Finally, we have the path cost. This is a function that assigns a numeric cost to each action, accounting for staffing, vendor fees, or reputational damage. Defining these 5 pillars turns debt collection into a solvable equation. The agent computes the sequence of actions that reaches the goal state while minimizing total cost. Without domain knowledge, an AI must rely on uninformed search strategies. Uninformed strategies use only the information available in the problem definition to generate successors. This illustrates an iterative deepening search at limit 3, exploring a decision tree by repeatedly expanding nodes layer by layer up to a set limit. While more efficient, its memory requirement still scales exponentially at the rate of OB to the D, where B is the branching factor and D is the depth. In a banking network containing millions of accounts and transaction edges, a breadth-first search would exhaust the available RAM and crash the system before finding a goal. Depth-first search offers a memory-efficient alternative. It explores a single path to its absolute maximum depth before backtracking to try another route. However, depth-first search is vulnerable to graph cycles. It easily becomes trapped in infinite loops, following circular flows that never reach a terminal state. Blind algorithms guarantee a solution on paper, but their massive computational load and rigid mechanics make them incompatible with global financial systems. To navigate at scale, an AI needs heuristics. Heuristics are mathematical rules of thumb that provide an estimated cost or distance from a given state to the goal. Banking institutions rely on these estimates to prioritize resources. Using credit score thresholds to bypass exhaustive background checks, or deploying simplified risk calculations are practical applications of heuristic pruning. Applying these estimates creates an informed search. A* evaluates nodes using f of n equals g of n plus h of n. G of n is resources expended, and h of n is the estimated cost to the goal. To guarantee an optimal solution, h of n must always optimistically underestimate the actual remaining distance. By consistently underestimating the actual remaining distance, an admissible heuristic allows the bank to safely prune millions of irrelevant paths, securing the optimal route without crashing the system. We observe the failure of blind search and the necessity of heuristics in anti-money laundering operations. Malicious actors frequently utilize circular fund flows. They bounce capital back and forth across multiple accounts to hide the illicit origin of the money. An uninformed depth-first search would enter this transaction chain and get permanently trapped following the loop, returning no actionable intelligence. An informed search bypasses the loop to identify smurfing, breaking large sums into multiple small, structured transactions to evade regulatory thresholds. The heuristic evaluates these transfers, applying a high threat score to paths exhibiting this structuring behavior, prioritizing them for human review. In fraud detection, algorithm selection determines the outcome. It provides the difference between catching a cartel and losing the trail in a computational bottleneck. Fixed pathfinding works for definitive goals, but many challenges, like portfolio optimization, lack a single perfect end state. Optimizing a portfolio requires navigating a stochastic market. A stochastic environment is one where variables randomly fluctuate and asset covariances produce high levels of statistical noise. When calculating a perfect global path is impossible, agents rely on local search strategies like hill climbing to navigate the fitness landscape. A hill climbing algorithm iteratively improves its current state. It evaluates neighboring states, discards lower returns, and moves towards the highest localized peak of yield. To manage risk during this climb, the agent employs a meta-heuristic technique called branch and bound. Branch and bound is an optimization method that calculates upper and lower limits to rule out invalid paths. By setting strict mathematical limits, the algorithm severs and discards entire sections of the market landscape that violate the bank's maximum risk tolerance. Meta-heuristics grant financial institutions the capacity to optimize returns aggressively, even when the market environment remains unpredictable. While pathfinding focuses on the route, regulatory objectives focus on the final state. This requires identifying a configuration that satisfies dozens of interlocking rules simultaneously. This is a constraint satisfaction problem, or CSP. A CSP is an AI framework focused purely on identifying a state that meets a set of complex interlocking rules. The Basel III Global Regulatory Framework effectively operates as a massive live-fire constraint satisfaction problem for modern banking institutions. The variables in this system are the diverse assets on the balance sheet, such as corporate loans, government securities, and retail deposits. The domains dictate the allowable monetary values and maturity profiles for those assets, as well as their specific risk weights. Finally, the constraints are the statutory demands. Metrics like the liquidity coverage ratio force these variables to balance perfectly, ensuring the institution survives short-term liquidity stress. Managing a modern bank relies on matching these specific search strategies to the underlying market reality. Heuristics allow an agent to prune the impossible, while constraint satisfaction ensures the final balance sheet remains compliant with global law.